Hello and welcome to 24th lecture of course on corrosion, environmental degradation and surface engineering. The topic of this lecture is a failure or fault analysis. Now, most of the books they refer only failure analysis, but I have added one new word here, the fault analysis. Why I have added, I will be explaining in today's or maybe this lecture. Now, we will go back to the first lecture when I was describing about the overall framework of the course. We say it will have a 5 segments: surface degradation we have covered, relation to environment we have covered, characterization technique, most of the technique we have covered in this, which are very important. Few will be also covered in maybe when we start surface engineering related topics. Now, in present lecture we are going to start this failure analysis, life cycle assessment, and we already have covered failure modes. We need to cover life cycle impact assessment. Whenever we think about the life cycle assessment, we need to know what is the residual life of the component. And finally, what will be the economic assessment. Now, if I want to do really maintenance of some system, will that be a cost effective, or replacing whole system will be cost effective. So, these points are necessary to take any decision. So, for the decision making, last time we started a data driven approach. We say when we have a data, then we can take a good decision. We do not have a data, suppose we have only models available, but that will not be sufficient to take appropriate decision or dynamic decision. Most of the decision which will be based on the model, it will turn out to be a static decision. Maybe those decisions are good for the today, but what will happen after 2 years we will not be able to estimate properly. So, for that purpose we require data and then data driven approach to take a proper judgment, proper decision. So, in this module we will be covering this the topics, maybe it will be covered in 3 to 4 lectures, and we are just giving a highlight something like a failure analysis and fault life cycle assessment. However, in present lecture I am adding the word fault. Why? Again, as I mentioned, I will be describing in detail in the present lecture. Now, let us start what we have covered earlier. We covered almost the failure modes in 3 to 4 lectures. Lecture 7 we also covered creep. Lecture 11 we covered something like a synergetic effect of the wear, corrosion and fracture. And if you remember, we said that even the wear debris which is coming out of the surface, it should be treated as a fracture because it is getting separated from a main component. So, fracture becomes a very dominating feature or dominating failure mode, and even the corrosion will weaken the material or system, but finally the wear out the damage will happen because of wear or fracture. So, the corrosion is like increasing the effect or maybe increasing the intensity or severity of the failure or severity of the fracture. That way I am treating this the failure. Again, we study something like a fatigue fracture. We say there are 3 stages. One is a crack formation. Again, I am using the word crack formation, not a crack initiation. We know that initial cracks will be there in almost all the materials. There will be grain boundary problems, there will be some sort of additionally in the manufacturing related some problems. There will be some crack or maybe some length which may not be seen easily, but there will be cracks. But crack formation or which is really going to lead to the propagation side, we are differentiating that. So, we say the crack initiation, crack formation is like it has a sufficient length which is visible, and if you provide some energy, then it will be causing the failure. So, crack formation, crack propagation and failure, this is what we studied. Another thing we studied also, the crack initiation occurs mostly as a stress concentration point. if the components are made equally stressed, designed in such a manner, the more or less failure can be avoided. And another, as I mentioned, that there will be some sort of initial crack. So, material discontinuity will be causing some sort of initial crack. Another one is that there will be possibility of the some voids or micro cracks also, and that can be spread, or that will be spread if there is a cyclic loading. That means the strain and then the tension side, and then 0 or maybe negative side. Similarly, positive stress, then 0 or then negative stress. There will be, if there are cycles, and that the stress cycle or strain cycle or some thermal cycle, that will cause some sort of a fatigue, and that will cause a failure also. So, what we say that this is a, maybe the initial is only discontinuity in a material, then forming the micro crack, then spreading, and finally, it turns out to be the fracture. This is what we have studied in earlier lectures. We also studied something like a creep failure. We say that creep is basically slow, it does not happen initially or immediately, the way corrosion does not happen immediately, it is a slow process. Similarly, creep is also slow process. So, slow and persistent deformation, there will be continuous strain and the continuous deformation, and we say even the load is not varying at all. There is a possibility, while we were initially was thinking about the fatigue, whether the load continuously varies or strain continuously varies, or maybe some other parameter like a temperature varies. While in this case a creep, we are saying that the stress is a constant or maybe more or less steady. So, steady load, steady stress, but again we can divide in 3 stages. We say primary stage, mostly it is a high value. The way we have studied the wear, initially wear will be very high, then we get a steady value, then finally up on the other side, that is what we use the word bathtub curve. Similar kind of the happening in a creep also. We say in the primary there is a mostly initially high, but it will reduce over the time. Then secondary, it will be more or less steady, and tertiary, which is leading to the fracture, that means a significant failure possibilities are there. And this happens because of the excessive stress and temperature, and sometimes material properties. A few material are very sensitive to of the creep failure. We should not use those kind of materials. And one more positive point I want to mention, that if the material have a fine grains, then chances are reduced, particularly for the creep failure. Reason being that they will not be, if there is any crack, and then because there are fine grains, immediately it will get stopped at the grain boundary. It will not be able to penetrate unless there is a stress level is very high. So, this is what we say that in if the fine grains that get stopped or expansion stops by the interface at the void levels. Now, as I mentioned that we will be thinking about the fault instead of failure analysis, we want to go ahead with the fault analysis, and then I mentioned also that I will be describing in detail. So, there is a time to describe that detail. Now, we say what is really overall aim of this course. As such, we say that we detect the failure before it causes a breakdown or excessive wear or cause economic losses, and which causes even the environmental losses, environmental degradation. We should avoid that. So, what we really require? We require some sort of a sensing trend, or it can be time based, or it can be frequency based, and then it has to be the nomenclature or signature need to be known to us, because every part will have a different kind of behavior, every feature will have a different kind of behavior. So, that is what we see, the sensing trend or frequency that are specific to parts, their function, their design and stages of the wear. Like the ultra mild wear will have some sort of characterization, medium wear will have some different characterizations. So, if we go ahead with the trending analysis, the time based or frequency analysis, we will be able to dig out some sort of key points which need to be examined, which need to be recorded and plotted, and then we do need a needful. So, that is what we are using, that we record a data driven approach. Now, in this case, as I mentioned, the signal, it can be time domain signal, it can be frequency domain, or it can be combination of the time frequency domains. So, depends on the situation which signal will be more important, we can go ahead. So, this is two failure modes, as I say, with different kind of failures. what is really our aim? To detect the failure well in advance and then stop it if possible. And then what is really required for that purpose? We require some sort of a sensing units or sensing equipments or sensors, which can really give a different kind of signals, like a time signal, frequency signal or time frequency signal, and some sort of algorithms which will be help us to come to the decision. And as I mentioned, that data driven approach, we really require a good data, and then based on that maybe some good algorithms which can really provide a good result. So, last time in our previous lecture we discussed something like a PCA, which even though we have a 10 features initially, but finally we extract only 3 features or 4 features which are having dominating and playing major role, maybe 85%, 90% role, then I will not really think about remaining 7. So, those kind of data cleaning and then dimension reduction are important when we think about the failure mode analysis, or maybe the failure mode and detection of the failure and the remedies of those methods. Now, when we discussed earlier failure modes, we said that major failures, as I mentioned, that we showed the fatigue failure and the creep failure that has been repeated here. In this case, we say that most of the time the small fracture initiates the high stress location, which I also in the previous slide I mentioned. So, there will be possibility of notch, hole or surface defect, and this is a major thing. If we get a more like a fatigue failure, so we need to really see if there is any notch, or maybe we are making any hole or any surface defect or surface damage, or maybe there is some sort of surface feature which are required for some other purpose, but will enhance the fatigue failure. We know that SN curve can be utilized particularly for the ferrous material or and the ferrous material which have a basically infinite life, if we say the number of rotations are more than 10, maybe in the 10 is to power 6. So, in this situation if the life comes more than 10 is to 6, we generally use a word high cycle fatigue, and then if it is a low, it is not able to really see that much life, we call the low cycle fatigue, and where failure will occur at that level. And in previous slide I mentioned about the primary creep, secondary creep and tertiary creep. You can see here that primary creep, there is a sharp the slope is coming, that means immediately it will be coming to the kind of steady state position. This is steady state means kind of the linear curve that is can be seen from here, while in case of the ruptured or the instead of fracture, here we are using the word rupture, it is again a sharp increase in a slope. So, these are the points to be considered. Now, why we really require a fatigue SN curve, we generally say it really helps us to figure out what is the fatigue strength. And now, if we do experiment, we know that the fatigue strength can be determined where the really failure will occur, because there is a continuous decrease in a cross sectional area because of the cracks or maybe expansion, and the necking formation will happen in tensile stress, but in this case also similar kind of in the initial pores are there, or maybe initial cracks are there, they will expand and reach to the one critical limit where the effective area is much lesser than required. And in the situation, because of the lesser cross sectional area, material will shatter either in a brittle form or ductile failure, whichever and depends on the material, depends on the temperature, depends on other parameters. So, these things have been already described in the course. Then we mentioned something about the cleavage, or maybe the separation, or the ground, we say that the boundaries or grain boundaries with getting separation. So, those things were discussed, and then I am just picking up this slide, maybe these figures from ASM handbook, because they have a complete handbook on the failure analysis. And basically what we are talking is a separation or the decohesion, and that is a rupture. You can see here this the example of the gear, and what we are using the word, this is the landing gear, which failed because of the stress corrosion cracking, which was also discussed. So, stress corrosion cracking was one of the failure mode which we discussed in detail. Now, what we are able to see here, that because of the decohesion, there is a separation in the grains itself. So, these are the basically the planes or the lines where the failures will start and in a big way. Now, if you look at a much in a magnified way, what we are able to see that the failures are happening because of some reason. Now, corrosion was one of the reason, and another we also discussed something like a hydrogen embrittlement that had been shown in this figure 2, and in this is a zoomed area for this. So, what we showed in this that this material is AISI 8740 steel, and in this in the nut formation, this is basically nut, and then failure of that has been discussed. What we are saying in this case, particularly when the cadmium plating process started, and then sufficient and then the backing was not done, because of that whatever the hydrogen generated in the process, that remained there, and what we say the retaining hydrogen itself. Now, we know very well that hydrogen will retaining will cause a diffusion or maybe the spread near the grain boundaries and weaken the grain boundaries. Not only weaken the grain boundaries, even it can cause intergranular fracture also. So, these things we have already studied in the earlier case. The question comes, these are the kind of we see after the failure, where the failure had happened, we can study, we can provide a remedy after that. So, in the near future we can remove the then maybe we can modify the process, we do sufficient backing, maybe give a little more time, or maybe there is a some sort of the stress corrosion is happening, we avoid corrosion as much as possible. So, those things are there, but it is after the failure, it is not before that. And what we are talking about this domain of failure analysis, the fault analysis, we say before real failure occurs, can we act on that? So, what we really require some sort of sensing unit, that is what I have a previous slide I mentioned, we require the sensing units, we require the sensors, so that we get some sort of information. Information can be in form of the cracks, or maybe we have discussed so many anti-leak techniques also, where the information is derived and then correlation is made. Maybe we are taking some sort of vibration signal, but other parameters are derived from that. So, these are indirect relation. So, we are interested in sensors, we are interested in the direct relation, we are interested in indirect relation also. And how we get it? We get it from a literature. When we do a lot of literature review, we build principles on that, we build models on that. Again, after making a models, it may not be 100% sure that those model will work in most every situation. So, we really require updation on that. That is where the data driven approach comes. We can pick up the model, we can pick up the existing literature, whatever is established, and then give as a model to the sensing unit or maybe the computational unit or wherever algorithm we are making. And as we get a newer and newer data, can we modify those model which we thought are perfect initially, and then we continuously improve. Now, in different environment condition, as we had discussed already, that in different environment condition, the material will behave different manner, system will behave different manner, even the parameters will be interrelated. So, what will be the final result as such may not be same in every situation. So, that is why we really require a data driven approach from that point of view. Now, here we the three diagrams also shown, the wedge crack has been shown, here wedge splitting has been shown very clearly, and then now finally here we are also saying that there is a cavitation erosion or cavitation failure which are also visible in this. So, the failure modes are many, failure types are many. Question comes, are we able to convert to the digital form? Are we able to really come up with something which can be made available to the computer, or can we really make an automatic system for that purpose? So, that is a challenge, research is on, and then what we use often the offline system and online system, and we know that slowly we are trying to go from offline to online. Whatever I am showing features, it is after the failure, we detect the failure under SCM or maybe some other sophisticated microscope, and then we try to judge. So, these all failure mode analysis are basically offline mode, and what we are talking in the recent time, that can we really shift to the online mode, can we really give a system intelligence enough to take a judgment, take a decision as per the requirement. So, this is what is really required. Now, another interesting thing which I observed and I am including now in this lecture is basically indentation test. And when we have realized that when we do indentation test to find out what is the hardness of the material, how do we really think about that? So, maybe what kind of really requirements are there? We say indentation test basically finding the material hardness as such, this is a major important thing. However, if we in this case we will go ahead with some load and then some sort of indenter, and then hardness of the indenter will be much higher compared to the material which is to be tested, and then we keep it for the some time, and then this in this case particularly authors what I am sure referring author of the 2009 paper, what they said in this case nano indentation creep. So, they could figure out that using nano indentation we can find out also the creep behavior. So, this is the intelligence that from one main whatever they wanted to do, but they can derive the many other parameters. How? That is what I am trying to show, that what they say capped if the indenter is capped only for the 0.01 second, they kept it under load for the 0.01 second, they found some sort of star, you can see here star mark here. Now, if instead of the 0.01 second, if they hold for the 50 seconds, you can see that there is a growth, and growth is 2.6 times. The star mark will be much bigger in a size, and that is what we indicate that there is a creep behavior can be derived from this. So, not necessary every time we need to come up with a new tool as maybe the new sensor, we can relate with the existing sensor in a much better manner, and then we can drive the relation. Again, for that purpose data driven approach will be better or maybe the more useful. So, what in this case I am showing that the size of the indentation found in the creep test, they use a 10 millinewton load, and then what we are showing here the contact edges, you are able to see the contact edge here. This is the contact edge, this is the contact edge, this is the contact edge star form. So, this is a 3-point star, and then as the creep time increases, then this spread will be on a higher side, and it will get a bigger and bigger. So, that is what we can do, and in fact, more studies can be done in this manner. Now, one another thing I want to just refer, the ASM handbook has published a number of atlas for the different materials. So, I am not able to cover all the materials, every kind of the failure. So, that is why I am giving this as a reference, that this is what we call a atlas, and then atlas of the microscopic image. We are trying to show the copper alloy, and then we are showing the copper behavior at the different temperature. So, in this case the first ABC has been shown for the temperature 425 degrees centigrade, and then tensile strength only 20 megapascal, it is not a very high stress, right. So, in this case temperature is playing major role in this case, and you can see here the B has been shown in the zone form, and then we are finding very smooth surfaces, and these all of the failures. Of course, what they found the failure under this load, which is hardly any load as such 20 megapascal, and then they found the failure happening after 76 hours and 54 minutes, and the B and C have been shown as a failed one pieces. Coming to the another load condition, that just they increase the temperature by only 15 degree, 425 to 440, and they reduce also stress by 25%. And what is the results? The failure has come almost in the half of the time. Oh, sorry, failure is at 308 hours and 30 minutes. So, even increasing temperature, but in the decreasing stress, that the failure the time has increased 308 hours. Now, this 308 hours is almost almost 4 times of this. So, 4 times compared to this. Now, what is really happening? Now, again we really required, of course, as I mentioned that this is published in ASM handbook, and then we can see the images of the various materials. You can see the sensitivity. Now, temperature has changed only by 15 degree, and then what we are reducing the stress by 25%. So, instead of 20 megapascal we are going with a 15.5, but still the significant increase in a life is happening. So, this is what we say that residual life will be required, more modeling is required again by changing the parameters, temperature or maybe say stress level. We will not be able to predict so fast good results. So, that is why the data driven approach is required for this kind of work. And then we as I mentioned in this case particularly that the grain facets are oriented at a high angle compared to the tensile stress, while in this case the dimples which have been small which are not very visible because of the zoomed image, and they are generally caused because of the micro voids which are available in a material. As I mentioned, every material will have some sort of defect and micro voids will be available in this, and then when they come together, many micro voids get together, join together under load or maybe in a high temperature. What will happen? There is a more formation of the bigger micro void or maybe void, and then it can be treated as a dimple on the surface. Now, so that is why they are now coming to the real topic, which is the failure. How do we define a failure as such? We say system, or this definition also has been given earlier in a lecture. Is a system or component fails when it does not do what it is supposed to do, and then when it stop working, all the maybe other one we stop working altogether, maybe completely. And then we also defined in one of the slide, the failure means a loss of usefulness. Even the material whatever like what we say laptop, maybe around 15-year-old laptop. Now, in the today's results are different, and maybe the processing speed is much faster. We are using i9 processor, and maybe that time it is i3, then it turned out to be useless in that way. That also can be cause of the failure. However, we are not treating that way. And then another one is that performance drops significantly and complete breakdown. So, observing this phenomena is not difficult. So, I do not really require very sophisticated analysis for the failures. Usefulness has come down, I can be rejected, and then question comes performance drop has come, it can be rejected. So, failure detection will not be difficult. However, if you want to go ahead with the root cause, why it has started, root cause will not come unless I go in a multi-layer kind of structure, or maybe start with a one simple fault and then see how the fault has increased in a size, or maybe many fault together have caused the problems. So, in my view fault should be analyzed, failures are already there, and then we are trying to go back and then see from where the origin is started and then how failure has started from that point. So, in my view and the failures detection is not difficult, failure can be detected because it has not been performing well, and then only analyzing required a fault analysis. So, fault becomes a very big and important criteria for us, that if we are able to detect the faults properly, then detecting failure will not be difficult. Sometimes people say instead of the failure, or they use the word crashing up system, and then again identification will not be that difficult. Analysis will be a bit difficult because we do not know what is the root cause and from where it has started. And then we really required a couple of approaches to really detect that. Another sometimes people say use the word failure when it is not in serving the intended function. That is the same thing which has been mentioned over here. Now, what is the best control strategy to avoid the failure? We say identify a possibility of the failure as soon as possible. When the system is getting loaded, or maybe when a system start performing, and then if we are able to think about the possibility of failure, then it will be easier for to understand. That means, we really require sophisticated many features which need to be addressed and need to be really continuously seen that way. Now, detection of the failure is easy as I mentioned, but what will be the probability of the failure? Now, if I have 10 parts, I now have a history, if I have a database, I can see one failure has happened in 308 hours, other failure has happened after 500 hours, third failure has happened after 1000 hours. I can daily use a statistical method to figure out what would be the probability of the failure if I go with a new system, or maybe we use again data to come up with the results. So, this is we required a really historical data, we really required a failure data to do analysis, but again that will be completely mathematics. We may get exactly if there is even the 5% of the failure and the probability of failure, we may get 5% next time, or we get only 1% or we get 10%. So, we really require more sophisticated analysis. For that purpose, we require really key factors or key performance indicators, or what we use the word KPI, and then some sort of inspection procedures also, whether it should be entity, it will be based on the sensor, what kind of sensor we are using, those things are important for us. And then if we have that thinking in our mind that we go ahead with the best control strategy, and before any failure happens or it is going to cause a failure, we should get information and we do a corrective actions immediately. So, that is why we say that whatever the maintenance strategy which people have been using for the corrective maintenance strategy should be replaced with a predictive maintenance strategy. That will be discussed after 2 lectures. We say that we will be thinking about maintenance strategy, what is a predictive maintenance strategy, and we will cover a couple of the case studies on that. So, now we started with the failure, we are talking about the faults, we are talking about the detection of the fault. As I say, the detection of failure is not that difficult, detection of the fault is difficult, and we are maybe if there are data available of the probability of the failures, we can take as a initial one, or if there is a model based on that, we can take as a initial input for our work. And then we really look at the key performance parameter. If we do not have a clear idea what are the KPIs, I can take 100 also, I can really measure 100 and then do iterations, because every analysis is iterative in nature. I may think initially maybe vibration is going to play a major role, or maybe the acoustic is going to play a major role, or maybe the eddy current based the response is going to play a major role. We can think, this is a brainstorming, we can think a number of things in a mind, but what are the key parameters that need to come? As in previous lecture we already discussed the PCA, the principal component analysis. We need to figure out which components are really very important, which have a very high eigenvalue, which have a high impact values. So, those things are important, and we will be covering today one case study on that also. Now, as I mentioned about the failure, we can another thing comes, can I categorize the failure? So, we are talking about the categories. Can I say that there is a low chance of the failure? As I mentioned here, the probability of failure, low chance of the failure, medium chance of the failure, or last high chances of the failure. If I do not have a much knowledge, at least I get the rudimentary level or the initial level, I can start with low chance of failure, medium chances of failure, or high chance of failure, and then it is like a fuzzy logic, and we do not have a clear idea, but at least some vague idea, and we can categorize initially and then we can go to deep. So, fuzzy logic related parameters are also there, and that is rating kind of can be given initially. So, that thing also we will be discussing in next lecture, and then what we say that this can be developed based on the recurrence time of the times failure, that is mentioned in the probability of the failure as such. Now, what is a medium failure and how people categorize in 3? We say medium failure is something like if material or system is really expecting is providing the expected duration. If some system are failing after 3 years and then our system is also failing around 3 years, then I will say the medium kind of failure, it is not a low kind of failure, right. So, this is crude, we generally say low means so it is not failing. If 3 years and the failure is happening exactly 3 years, then it is a medium failure, it is not a low failure, right. Now, if 3 years is expected life and is failing in a month, then I say highly critical, at a critical level of this failure is very high. So, severity index is increasing in this form. So, this is these are the some terminologies we will be using in our next lecture, and then next lecture topic also I am defining is a failure mode and effect analysis, FMEA. And then we say this method is a systematic method to find possible problems in a process. we are using the manufacturing process or any process or assembly process and product or system whichever, right. So, FMEA can be utilized for all, and then we need to figure out what kind of the failure and how bad that failure will be. And as I mentioned earlier, we have already discussed about the failure modes. We need to really look at the what are the causes of those failure modes, which also we have studied to some extent, and then what problems have caused those kind of failures. Then if we do that kind of analysis, we can really prioritize the area in which improvements are required. So, again we take a data from in the past or maybe the history, we do analysis, based on analysis we figure out which area are very important and require our attention, require little more science to do needful things. So, these are important. Now, that is a failure which I mentioned. Now, coming to the fault, we see in engineering a system reliability, word fault means mistake in a design, and any flaw which is made either in a manufacturing time or maybe some other time, and then we may not be knowing that kind of fault, that is something like a hidden fault, something or something which is not visible to us, but it will cause a finally failure. And that is why we say maybe even the 5% failures are maybe happening because of the faults or hidden faults. If you analyze it and you find out 95% systems are success and only 5% failures are happening, quite possible there are some flaws in a design, there is some flaw in a manufacturing, there are some flaw in assembly, there are some flaw in a operation, or maybe some sort of human factors, that is possible. So, those things are related to fault, it is not related to failure immediately. So, what we say, any imperfection is also important in that case. Now, coming to the imperfection point or maybe flaw point or maybe mistake point, we need to really treat this as a fault. Now, faults could be leading to the failure, but as I mentioned that it will not show up immediately. So, immediately we will not be, maybe after a month, maybe after some duration it will come. So, I am just taking one example, something like corrosion in the brake line. The corrosion is happening often because it is open to environment brake lines, and then corrosion will occur there, right. Now, if this failure occurs, then naturally there is a need to really look at, if the corrosion is happening, what will be the life cycle of that component or system. So, that is why the fault and then detection of fault, and because of that fault what will be the impact on the life cycle, that is important, and that is why it needs to be assessed properly and then managed properly. Now, as I mentioned very clearly that fault is a hidden or latent problem in a system, it is a hidden problem and we need to diagnose. We have already discussed NDT techniques, we know that on the surface if there is any fault can be seen, but if there is some fault either within a surface or subsurface, then we have a number of techniques. So, then those techniques depends on number of sensors. Can we utilize those sensors in our way and come up with some new technique, and then we say fault diagnosis, and that is what we call many times the conditional monitoring, which will be discussed as I say next lecture. Next another one is there is an example as I mentioned here, corrosion in a brake line could cause a line to break, particularly under high pressure. When the area of the fluid is decreasing, naturally pressure will increase, and then because of that initially that the corrosion of inside what do you say the brake will not be visible, or even the pipe corrosion will not be visible, and the area is continuously decreasing, pressure will build up on that, and then which is not visible, but one day what will happen, the brake whole line will burst, and that is instantaneous or catastrophic failure, and then in that situation brake will stop. So, this is when the brake will stop means brake will fail, but if there is a fault initially that was not visible, and that will be a kind of the failure where what is happening, somebody is driving in the car at a very high speed and suddenly the failure of the brake happens, naturally it will be very dangerous for not only the person who is driving, but for other people also around them. So, this is what is important, and another is mentioned finally that identifying the fault and fixing it. Question comes, how do I fix it? So, there are number of methods also to fix it, that we will be learning few methods to fix those faults in surface engineering methods. So, that is possible, and system becomes a more if we are able to fix it, if we are able to identify faults and fix it, then system can be more reliable, safer and better, and that is our aim of the course, make the system more reliable, safer and better by utilizing, by understanding the failures, faults, and then do the remedial action, mitigation action, so that overall reliable, safer and better system can be given to the society, which will cause lesser environmental degradation and overall win-win situation. So, for that purpose what we really require? We require a modeling, we require a signal capturing and processing, and finally computational intelligence also need to be added in a system. So, these are the important items, and then that is mostly related to the data driven approach, because the modeling we have initial, and then that will also give a kind of the comparison, because whatever we get a new data need to be compared with something. So, that is why this modeling will really be helpful, and this modeling comes from a previous data up in the previous knowledge only, and then comes the signal which we are capturing using the sensors that need to be processed properly, and then if we process and then do computational maybe say like a PCAU, or maybe the other artificial intelligence units, or maybe the algorithms, so that it will turn out to be very useful, and finally we want that. Now, so what I say that when any feature or parameter of system deviates from expected value, this is what I mentioned here, the expected value comes from previous experiences, comes from history, comes from data, which is maybe it comes from the graphs. We learned something how to digitize the graph and how to utilize it. So, expected value will come from that. Say material is supposed to give a 300 megapascal, and that is naturally been verified, and the data have been really available in the type book, that is why we are getting. So, that is the expected value, right. And then when expected, and then any time that we are using sensors, and then we find any deviation from expected value, we say there is a chance of the fault. Now, there is a possibility of the noise also, that is why we use the word signal processing will be required, right. So, fault, and then if we do signal processing, we remove all the noise, and then still we find a deviation compared to the expected value, we will say there is a chance of a fault. So, diagnosing fault using this kind of sophisticated devices, or maybe sensors, processor, and then the right algorithm will be able to identify the faults, and that is what we really require, and that is the main tool now in maintenance engineering. So, that will be done. Of course, this will also, as if we are able to find the fault, it will also help us to find out the degradation tendency. If the fault is increasing very fast, not increasing at all, it got halted because of as I use of an example, if you go for the very fine grain boundaries or grain structure, possibility is that the fault started and immediately got halted, it is not really able to penetrate the other grain. So, it is along the surface of the grain or along the boundary of the grain, it is not really increasing the fault as such. So, there is a possibility, and the overall aim of this course is basically to go ahead with good identification of fault and the removal of fault. So, that is why we say this the topic failure analysis basic aim is to go ahead with the fault detection and diagnostics. So, that is why in short many times people use the word FDD. So, we will be going with the fault detection, we are not going with the failure detection, we are not going with the failure analysis. Failure analysis will happen. If we are having a reliable FDD, then failure analysis will come its own, right. So, this is important, and then sometimes people instead of the FDD they use a word of fault diagnosis and health monitoring. That is why I use a word. Next to next lecture we will be giving on the conditional monitoring the units, and then it will be highly related to each other. Now, FDD approach As I mentioned here, we require modeling, signal processing, computational intelligence. So, FDD approach can be model based, online data driven technique, or it can be knowledge based. So, initially we can start directly if we have a historical data, we can go ahead with a knowledge based data, maybe say some sort of model. That is why the modeling is required. However, if I do not have anything, I totally made a totally new thing, then quite possible initially the samples will be made and some data will be generated, and based on the data we can really make a approximate model, and then we continuously refine that model. So, that is also possible. So, our main aim in this section is going ahead with the FDD, something like a fault detection and diagnostics, and then possible give a remedy using the surface engineering knowledge. So, this is what we say monitoring the faults. How do we go ahead with the monitoring the faults? It is analyzing the fault or the malfunction, as I say, it is not really is deviating from expected performance, fault level, not a failure in a level as such. In a system, a process can be made easier by using the data driven approach, that was I described. Now, what we really required initially, as I said, if we have a data, it will be always helpful. So, include past data so that we can draw some sort of conclusion based on the relationship. Now, it can be regression analysis, it can be some other analysis. So, that we really required relationship between the different inputs and a specific value occurrence. So, most of the NDT techniques are based on this, they have some sort of relation established, and then whatever they are measuring, they are able to drive some other form, maybe result, they are able to drive the results based on that. Now, we say that the gathering relevant information about the analysis must be starting points. So, the literature review, literature documentation, and then initial model which are available in literature must be understood and must be utilized. Now, as I mentioned, the regression analysis and then correlation also we studied last time may be employed along with a more modern approach, something like a clustering and classification. So, what is a classification? If I know the failures are in 5 different kind of failures. So, what is the really appropriate KPI for that the failure 1, failure 2, failure 3, failure 4, failure 5. Now, 6 failure if I get, I try to give in one of the kind of the bucket, okay, failure 1 bucket, failure 2 bucket, bucket 3 bucket. So, this is basically to classify the different kind of, like, if we say there is a crack 1 bucket, or crack is a 1 class, or we say that pit is another class, or we say dimple is another class. So, whatever the KPI related factors, if we are able to measure, we can keep in those. So, those things are less in the recent one, and this really required a machine learning algorithms to go ahead with the clustering and classification, and we will not be able to cover these topics in the present course, but we will just highlight a few features and maybe one case study. So, when we say the sensor data, operational parameter, maintenance records, environmental factor, all should be reviewed. So, if you are really want to go ahead with the fault analysis, we really require all, we not only the sensor data are sufficient, or maybe we really require operational parameter, because we need to develop a correlation, what is really the sensor is giving and what is operational parameters. And then if there was some maintenance, or maybe some the duration of maintenance after 3 years, 6 years. So, those histories also will be important. And what is the really environmental conditions there, what is the humidity, what is the temperature. This is the reason why there is a variation in the performance of the different materials, and one system is working well in one situation, but it is not working well in other situation. So, those things can be dig out using this kind of data, and that is very important for data driven approach. What we use the word that we really require data driven approach. Now, what we mentioned another one, that and then the pre-processing of the data is required. So, when you do the pre-processing, mostly we try to denoise it, we remove the noise, and then sometime if some data have not been recorded, we do some sort of interpretation also. So, the missing values will be given, and somewhere we get some random out the very high value kind of thing. So, remove outliers also, and then every variable in last PCA also mentioned that we need to go ahead with the standardization, because we are not going to deal with only one variable, we are dealing with many variables. Whenever there are many variables, standardization is a must. And then if there is any constructive features coming out of that, or maybe the new feature which we need to be diagnosed, that need to be highlighted. Now, once a model is been made, then what we do some sort of a training to model, so that it is really meeting the expectation, it is giving the good results and confirm. After that, whatever the predictive analysis can be performed. A predictive analysis in the future, we are trying to predict what will be happening tomorrow after that, and the whole predictive maintenance is based on this kind of principles. Now, we can say that if we keep getting more and more information, naturally we will refining our model. So, naturally we need to have algorithm which can continuously refine the model and improves the ability to foresee or explain the potential failures. So, this is the main thing. If we are able to monitor the faults, and if we are able to utilize a data driven approach, and we are able to make a predictive model, and we are able to continuously improve that model, we will have substantial benefits. We can really minimize the surface degradation, environmental degradation, even the corrosion, but for that purpose we really require this kind of approach, which continuously get updated, because everything is iterative. If we do not update, whatever we design today will not work tomorrow. So, that tomorrow case also need to be judged and then need to be updated. So, what we see when looking for the ways to improve a system, procedure or product design, whatever I mentioned, fault analysis must be utilized, and it is itself is an iterative procedure, and as a newer thing keep coming, we need to incorporate in our model. So, that is why we say data driven approach to the fault analysis, and then whatever we are learning from some sort of fault failures or and then the failures will be useful for the improving the reliability, quality and performance. So, this is if we are able to really make up, or we are able to really go ahead with data driven approach and then finding the faults, and then go ahead with the surface engineering to really bridge those gaps and to minimize the faults, then the purpose of this course will be completely fulfilled. Let us take one case study. What we are trying to say that fault monitoring, as I mentioned, is important for us. We are trying to do a fault monitoring using the principal component analysis. PCA was described in previous lecture, and what in this case study has been picked up from literature, which is a paper which was published in 2003, and then they try to extract the feature and classify the gear faults using the principal component analysis. That is I am trying to give one case study in the next few slides. So, what they compare is something like a gear which can be healthy, normal operating condition, or it can be faulty. Now, faulty can be something like it has some subsurface crack, naked eyes we will not be able to see, and the broken teeth which with naked eyes we can see. So, here we can say directly this is leading to the failure, and this is leading to the fault, maybe the diagnosis of fault. So, faulty gear can go ahead with the failure, right. So, this is what I am trying to mention here. Now, what diagnostic information for the categorizing the gear failure using principal and the PCA, they try to use a vibrational signal. As I say that we really required some input. So, they use a vibrational signal using accelerometer, and then they did perform experiments, and that too on an industrial gearbox, and then in a hope that PCA will be able to differentiate gear faults. So, this is what they use the PCA to differentiate gear faults. If normal gear is a case 1, maybe say the cracked tooth has a 2 and the broken tooth has a 3. So, crack one and the normal one, normal cracked one and the broken tooth, they are 3. Now, this is a complete gearbox, as maybe the sketch of the gearbox has been shown here. Here Z is a number of teeth on the gear, and then F is a kind of frequency, and then that is what we say the number of times gear comes in a contact, a gear teeth meet. So, this is the frequency kind of thing is being given, and then what they chose as parameters, one is a temporal one and another one frequency. So, they measure the data, accelerometer data, they did a pre-processing, and then based on that the feature selection, and based on the feature selection they went for the fault classification. Of course, there are not too many faults in this case, there are only 3 cases, one normal gear tooth, and then the cracked tooth and the broken tooth. So, this is what they showed, and then faults detected or fault diagnosis. There are 2, one is a detection and from where it is coming, what is the really purpose. So, for that purpose we really required the features, like in this case the time dependent feature, the temporal feature, another one is the frequency based the features has been shown. Now, if I go with only the time dependent, we have a mean value as a time, standard deviation time dependent, skewness, kurtosis, and they are the time dependent statistical features. So, this is what they try to calculate the 10 parameters, and then they capture the raw data, as I mentioned, the vibration data, and those data with the amplitude versus sample point have been shown over here. Now, you can see here that this figure the vibration level is relatively low, while in this case some places vibration is increased, right. Even look at the vertical is 0 to 500 and 0 to minus 500 the same. While coming to the broken tooth, we are able to see they have plotted, instead of the 0 to 500 they plotted 0 to 1000, right. So, 0 to 1000 and 0 to minus 10,000 minus 1000, and then you can able to see at the every after some period we are getting some peaks. So, some sort of characteristics frequency is visible over here in this case. So, they did online measurement, we can get all the data, and then 3 operating condition, as I mentioned, normal condition, cracked tooth condition and broken tooth, and then they use all the non-dimensional factors, non-dimensional parameters. We know that in PCA we require standardization, even though these are all the factors, they are non-dimensional. Non-dimensional is a one thing, but standardization is another thing. So, we really require standardization if we are getting the data. This is the gear vibration data, even though we have data. So, first is that we try to calculate what are the KPIs which we have used. In this case, mean value, standard deviation, skewness, kurtosis, max peak value, that is what has been mentioned, and then RMS value, crest factor, shape factor, impulse factor and clearance factor, and then these values they try to figure out. They collected 23 data sets for each case, 23 data for the normal case, 23 data for the cracked tooth, 23 data for the broken tooth, and the only thing they kept a sampling frequency same, maybe operating speed was the same maintained, that is why they kept a sampling frequency same. Now, what was the problem for them? They say that there is a overlapping, the overall signals they are not able to identify by looking at direct signals, right, and then even when they try to extract the features, then and all the features they found there are a lot of overlap. So, they were not able to extract the much out of this. And then what we did because they have not given the data. So, what we did a digitization of the graphs which they have plotted, and based on our MATLAB coding, we try to get those data, kurtosis value. So, you can see that in the 9 plots, 10 plots here, 10 features. So, feature 1 is a standard deviation, skewness, kurtosis value, maximum p value, mean value, and everything has been written in the MATLAB code. And then we can see here that this data is basically for normal gear feature, for the cracked feature or broken gear tooth. So, these have been vertically plotted, and then sometime we are able to get a very closeness, something like normal gear and a cracked one, you can see the features are almost merging in this case, right. While in this case particularly there is a separation here, the green and red are matching, and what is the green? Green is basically broken teeth, and the red is for the cracked one, and the blue is for the normal one, and that has been also mentioned here, normal, cracked one and the blue one. Now, we see most of the times the normal and cracked one are really superimposing each other, except in this case you can see in the kurtosis value, the normal gear value has a very high, right. Otherwise, more or less all other graphs we are showing that normal and cracked one are they are almost matching, or maybe not very significant difference which can be we can really say this is a feature different, maybe significant difference in that. While in this case of the green line you are able to see there is a separation more or less almost in all the cases, except as I mentioned in the kurtosis value here, and then one more here where is the super, and then the skewness also we are able to see a lot of overlap. Now, we try to do standardization. When we do standardization, we know very well how to go ahead. With the previous lecture it was mentioned. When we go for the standardization, and we are again plotting it. So, standardization basically instead of going for the very high value, in this case you look at that 115 to 165, minus 1.5 to 1, 0 to 30, 200 to 1400, 70 to 130. In standardization more or less always is something like a minus 3 to 3, minus 3 to 3. So, these are the all features. The only question comes when we are going for standardization, and then we find almost all it has becomes a more like all curves are really merging with each other. It's not we are not able to differentiate much. There is a kind of the superimposing happening. So, standardization we know very well that standardization is important to keep mean value 0 and variance as a 1, it is important, so that we can really figure out which parameter is playing major role. Now, here without PCA we are not able to figure out, but you can see the vertical axis by and large vertical axis is same, and horizontal of course we have a 23 points. So, horizontal is same, vertical is also same. Now, we need to use a PCA to separate the importance of which is the more important, or maybe use a PCA or use the eigenvalue to figure out the eigenvalues and then go ahead with a descending order. So, in this case first to go ahead with the PCA, the first thing is that go ahead with the covariance matrix, and then covariance matrix we know very well is basically relation among the members or maybe the features. So, what is the relation of the first feature with the other feature, second feature 0.19, what is the feature 1 and feature 3, maybe the parameters 0.31. So, this is what and been shown. Now, feature 1 and feature 5 is 0.95. We know very well the diagonal is basically variance, and variance has to be equal to 1. As I mentioned, the 3 characteristic mean value after standardization should be 0 and variance should be 1, and when coming the covariance matrix then diagonal should be 1. So, these are the kind of the cross checks, and all MATLAB code have been utilized for this purpose. And then as I mentioned here that covariance matrix and then this diagonal term of the covariance is same equal to 1, because 1 to 1 feature 1 and feature 1 they will have a equal to 1 relation, they are 100% matching, feature 2 versus feature 2 100% matching, feature 3 versus feature 3 100% matching. So, it cannot be other than 1. Now, when we go ahead with PCA and then we try to arrange in the descending order. So, first eigenvalue comes top on that is a 0.3, the last value is a 0.02. You can see here more than the 0.51 is something like 5 features, and the remaining other 5 they are not really useful as such. So, one way is that we can really simply reject this 5 eigenvalue and we say principal component of 5, or sometime people say no, lesser than 1% I do not really care. So, we can go ahead with the D1, D2, D3 also. So, remaining all other parameters eigenvalues are lesser than 1, it can be. However, often we go ahead with a percentage base. So, that is why that has been shown a percentage. First eigenfactor shows a percentage of the 54.6, second eigenvector shows 18.02, third eigenvalue is 10.31, fourth is 8.69, and the fifth one is a 5.62. So, what we say that okay 5% either you go ahead with the more than 5% or total summation should be more than 95%. So, this is a total summation of the 5 features turns out to be 96.88%. However, it is a subjective, people can think about 85%, 90%, while in this case we have selected the top 5 eigenvalues, and based on that we can try to recast the data. When we go for the recasting the data and then again plotting, then we can see here very clearly that after plotting first eigenvalue related first parameter, second parameter or second feature, third feature, fourth feature and fifth feature. So, here the everywhere you can see the clear differentiation between the green line and the 2 line, green line and other 2 lines. So, that is indicate very clearly that the broken tooth signatures are very clear. We are able to diagnose very clearly without any problem. If we go back to the previous one, here we say that except the skewness and kurtosis, we are able to differentiate, and of course, in the RMS value also we find some sort of superimposition, while new 5 features we are able to see clear division. Now, coming to the this cracked one and the normal one, we are also able to see some sort of separation. So, feature 1 we are able to see separation, feature 2 we are able to see separation, feature 3 we are able to see feature 5 we are able to see separation, while coming to the 3 and 4th feature we do not find that kind of a variation. Now, I can think about 2 ways. One is that maybe there is a subsurface crack and then vibration signal is not good enough to pick up that signal, and we need to change the sensor, or maybe we get another kind of sensor to get a better response, or maybe we go ahead with the next stage of the processing. So, PCA is a one technique which we have used, but we should go for some other techniques so that we can filter out those things. These are also important and we can think about that. Now, when we plot on the 2 axis or 3 axis, these are the plots here. You can see here the somewhat separation. Blue color lines are visible, there is a separation here, green color lines are separation. So, gear faults on the using only 2 the principal component, gear faults using 3 components or principal components, while in 3D plots we do not find much advantage, we are not able to really differentiate. But 2D plot we are able to see, there is a separation of 2D of the broken teeth, the normal teeth and then the cracked teeth. Now, this is again kind of we really require some sort of additional processing on this kind of signals, because broken teeth we are able to separate, but somebody says that the fault is crack is a fault and we need to diagnose properly. That cannot happen with using this kind of signature or that kind of vibration analysis and PCA. We require little more sophisticated method to go ahead or maybe get a better results. One the question comes, can we go with a multiple time of the PCA? So, that does not really help. This is the first PCA which has been done. If you go for the second PCA, we do not find much difference in the principal component. So, it should be rejected. We say the sequential PCA cannot be utilized. We really require some other method to come up with a better and better results. So, we will continue this topic in a next lecture, and mostly it will be the failure mode and effect analysis. We will highlight that, we will cover 2 case studies in that lecture. Thank you for your attention.